Twinkle Twinkle GPS, presented by Science at NASA. Go outside tonight and behold the stars, especially bright stars low on the horizon. They twinkle as irregularities in Earth's atmosphere pass by. Unseen to the human eye, the same thing happens to signals from GPS, the Global Positioning System. Radio signals twinkle in much the same way as bright stars appear to do at optical wavelengths. This can have effects on GPS, causing the signals to brighten and fade and reach Earth at unpredictable times. All of this could degrade the accuracy of GPS positioning. The twinkling occurs because signals beamed to Earth by GPS satellites pass through a layer of Earth's atmosphere called the ionosphere. Irregularities in the ionosphere, referred to as ionospheric depletions or bubbles in the science community, span the hemispheres at the equator and are a major element of the low-latitude geospace region. Dynamic and beautiful, these irregularities form huge horseshoe arcs between hemispheres, with their apexes centered on the magnetic equator. Studying this phenomenon is the main reason NASA conducted a mission called CINDI, the Coupled Ion-Neutral Dynamics Investigation, beginning in 2008. The CINDI instruments were carried into space along with other instruments on board an Air Force Research Laboratory satellite called the Communication Navigation Outage Forecasting System, or CNOFS. CINDI was designed to measure ionization of the upper atmosphere, including the irregularities that cause GPS twinkling. The behavior of the irregularities responsible for the GPS twinkling turned out to be quite surprising. Rod Helis, principal investigator for CINDI at the University of Texas at Dallas, explains. According to conventional thinking, the ionosphere becomes unstable shortly after the sun sets. As darkness falls, ionized atoms and molecules begin to recombine into a neutral state. During this transition period, 1 to 2 hours after sunset, irregularities are quite strong. As the night wears on, however, those irregularities were thought to fade and eventually vanish around midnight. But that's not what CINDI found, says Helis. There were indeed many irregularities around sunset, but they did not vanish around midnight. On the contrary, there was another peak in irregularities during the middle of the night. This second peak has appeared most pronounced from June through August. Scientists aren't sure yet why this second peak occurs or why it varies by season. But Rob Pfaff, project scientist for CINDI at NASA's Goddard Space Flight Center in Greenbelt, Maryland, says, this unexpected behavior is a key discovery. It shows that the ionosphere can still surprise us. Researchers still have much to learn about the ionosphere and how it can affect GPS and other satellite systems. CINDI re-entered the Earth's atmosphere in November of 2015, getting a one-of-a-kind close-up look at the ionosphere before it disintegrated. Pfaff adds, towards the end of the CNOFS mission, we had this great chance to measure the ionosphere at much lower altitudes than we did previously. In fact, we were able to see shear in the motions of the upper atmosphere, areas where the ionosphere at lower altitudes flowed in the opposite direction to that at higher altitudes. We think the shear may be one of the causes of the GPS twinkling. Next up, says Pfaff, is ICON, the Ionospheric Connection Explorer, due to launch in 2017. Led by researchers at the University of California, Berkeley, the goal of this NASA mission is to understand the tug-of-war between Earth's atmosphere and the space environment. Like CINDI before it, ICON will learn a lot about what causes GPS twinkling and much more. Stay tuned for updates from the edge of space at science.nasa.gov.